Okay, so in the last lecture, we derived the defining equation that gives us the vector fields x, for which the integral L of x, y, y dash is left invariant. So this integral is left invariant under a vector field x if x1, which is the first prolongation on x, on L plus L times the total derivative of xi with respect to x equals df dx, where f is a function of x and y, a gauge term. The two derivatives with respect to x are total. Here x is the vector field of the form xi d by dx plus say eta d by dy. Right, so we'll determine the vector fields that leave a specific integral invariant in which, say, the Lagrangian, the integrand of that integral, is a half y dashed squared minus a half y squared. If we do the Euler-Lagrange on L and put it equal to 0, as I recall, what we get is the differential equation y double dashed plus y equal to 0. Remember from the previous chapters, this differential equation has 8 vector fields that leave it invariant. That was given as an exercise. Here we are not determining the vector fields that leave the differential equation invariant, but rather we leave it determining the vector fields that leave this integral invariant, and the manner in which you do that is that equation there, where f is the gauge term. Right, so if L is equal to a half y dash squared minus a half y squared, then x1 on L will have the following form. So here then, let's put in the various terms. X1 on L will be equal to xi dl dx plus eta dl dy plus eta prolonged dl dy dashed. Put in this L, there's no x, so the partial derivative is 0. The derivative of L with respect to y is minus y partially. The derivative of L with respect to y dashed is y dashed. And therefore, in this equation, that is this defining equation here, if we put in all the x1L, etc., what we end up with then is the following. So therefore, we get the following. We get minus y times eta plus y dashed times eta 1 plus L is a half y dash squared minus a half y squared, and then we've got the total derivative of xi with respect to x equals the total derivative of f with respect to x. Right, and then we're going to prolong, at least we're going to prolong, put in the formula for eta 1. I'm going to write total derivative of xi with respect to x in terms of partial derivatives, and so too with df dx. Xi is a function of x and y. F is a function of x and y. Eta is a function of x and y. So what we get is the following. So this is minus y times eta plus y dash times eta 1. Eta 1 in terms of partial derivatives is eta x, partial derivative of eta, plus y dashed eta y minus y dashed times xix minus y dash squared xi y. Then adding in a half y dashed squared minus a half y squared, that's your L. Writing the xix, the derivative of xi with respect to x in terms of partial derivatives, that is partial derivative of xi with respect to x plus y dash the partial derivative of xi with respect to y. And then the right hand side, partial derivative of f with respect to x, y dash partial derivative of f with respect to y. So this is then an equation involving partial derivatives of the unknowns xi, eta, and f. Since f, xi, and eta are functions of x and y only, their partial derivatives in this equation are functions of x and y only. So as before, when we did similar calculations, we can separate by powers of y dashed. And what we get is the following. First of all, if you look at the terms involving y dashed cubed, right, it's clear that we get, what do we get? We get minus xiy, if you go through that, plus a half xiy equals 0, and this implies that xiy is equal to 0, and that implies that xi is a function of x only. Let's suppose xi is a function like this. A is a function of x only. So we can remove all the terms involving xiy because xiy is 0. Then putting in the y dash squared terms, if you go through that, what you end up with is an eta y, just go back to the defining equation, minus xix plus a half xix, which is half the derivative of xi with respect to x, and the right hand side has no y dash squared term, so that's equal to 0. So that implies that xiy is equal to a half xix, and of course xix, why can we not write that nicely? This is xix. Since xi is a, xix means the derivative of a with respect to x, that is eta y is a half a dot. Dot is derivative with respect to x. And then the left hand side could be a function of y, but the right hand side is only a function of x. So as far as this derivative with respect to y is concerned, the right hand side is a constant. So we can integrate both sides with respect to y. So we get eta then is, if you integrate with respect to y, this is equal to a half a dot. Integrate that with respect to y, you get this thing times y plus an integration constant, but the integration constant could depend on x. Say it's b of x. That then is eta. We substitute this into the terms involving y dashed only. Now before we do that, if you equate the terms involving y dashed from the left and right hand side, you get eta x equals fy. In fact, if you just go back to the defining equation, you notice that the right hand side involving y dashed is that term there, so the right hand side is y dashed. If you check out the left hand side, you get what we have earlier on. Right, so what is this? This implies that fy, f is an unknown for now, eta x on the left hand side, I'm writing that on the right hand side now, is the derivative of eta with respect to x. So we take this eta and you differentiate it with respect to x and slot it in here. You differentiate eta with respect to x, you get a half a double dot y plus b dot. And then integrate the two sides partially with respect to y. So you get fy is, if you integrate the y, you get y squared over 2. So this becomes a quarter a double dot y squared. B dot is a function of x only. You integrate that with respect to y, you get b dot times y plus an integration constant which could depend on x, which is c of x. What's left in the defining equation are the terms independent of y dashes. So if you integrate, or rather if you put in the terms involving those independent of derivatives, the left hand side, it turns out, is y times eta, we have a form of eta, minus a half y squared xi x, and the right hand side is f differentiated partially with respect to x. We have a form for eta, xi, and f. So, i.e., what we get here is the following. So it's minus y into eta. Eta at this point is a half a dot y plus b minus a half y squared. Xi is the derivative of xi with respect to x, which is then very simply a dot. And on the right hand side, we have f differentiated with respect to x. That's f differentiated partially with respect to x, which we are going to get from there. So if you differentiate f partially with respect to x, you get a quarter. A triple dot, 1, 2, 3, times y squared plus b double dot y plus c dot. And from this equation, you notice that the unknown functions a, b, and c are functions of x only, so we can now separate by powers of y. So in that equation, if we separate by various powers of y, first of all, this y squared, that's the highest power, we get minus a half a dot minus a half a dot equals a quarter a triple dot. That comes from the right hand side. So we get therefore a triple dot plus 4a dot equals 0. And this looks like an ordinary differential equation, which remember in d operator form is d cubed plus 4d on a equals 0. We get d into d squared plus 4 operating on a equal to 0. And remember then, if we know the roots of this operator, we can write down the solution for a. Capital D means d dx. The roots of this are, well, 0 and 0 plus minus 2i. Right, so the solution coming from 0 will be a constant e to the 0 times x, and the solution that comes from the complex roots are e to the 0x into a constant cos 2x plus a constant sine 2x. So let's write down the Therefore then we can get a to be equal to a constant, let's call it constant capital A, that comes from the 0 root, plus e to the 0x is 0, the real part. It's b cosine 2x let me write that 2x nicely, plus another constant called capital C sine of 2x. Looks like a child writing. So we have the a sorted out. That is from the coefficients or the equating the y squared terms. Right, now equating the y terms. So if you get y to the 1, on the left hand side we get minus b equals right hand side is b double dot. So we get therefore a b double dot plus b equals 0. And similar to above, we get therefore b is equal to some constant cos 2x plus another constant sine 2x. And lastly, we get c dot equals 0, and this means c is some constant, but little c does not feature in any of the xi's and etas, so it's not going to give us any vector field. So this is actually redundant, the value of c. Right. So we've got a, b, and c. We're going to substitute this into the vector field. Recall that the vector field is equal to xi d by dx plus eta d by dy. We now have to write down xi's and etas, and corresponding to each vector field there is also a gauge term. Right. So as we did before, we write down the forms of xi, the form of eta, and this time the form of f also. Right, so let's do that. Right. So now we get, putting all of this together, xi is very simply a, which is capital A plus b cos 2x plus capital C sine 2x. This is that xi there. Eta, from its form, I'm just going to write down the form, if you go back, is a quarter y squared, if you do the calculation, into minus 4c, capital C, sine 2x. Just go back and do the calculations, minus 4b cos 2x plus y into capital E. This is the form of the b function, which is cos of x. Where's my eraser? So this is cos of x. That is E, of course, and minus d sine 2x. So let's just do that. And this is then minus d sine x. Just a matter of going back and putting in the numbers. And what we don't have when we're doing the vector fields of differential equation is this gauge term. So it turns out that when you put in the f, let's just go back to see what f looks like. F has this form here again. And if you put in the forms of a and b dot c, put it equal to 0, what we get is the following. Oops. Right, let's write down f from that statement. we get f is a quarter y squared into I'm sure I made a mistake. Let's just go back. The form for eta is wrong. In fact, let me just make some adjustments here. It turns out that this in fact is f. Sorry about that. And if I have to do the eta again, it turns out that the etas, sorry about that, eta is actually equal to a half y into 2 c cos 2x minus 2b sine 2x. This is after differentiating these things, plus capital D cos x plus e sine x. Right. So how many constants do we have? We have constants a, b, c, d, and e. So there are 5 constants in xi and eta. Let me just identify xi. That forms part of the vector field. Eta forms part of the vector field. And in these two things, there are 5 constants. 5 constants means there are 5 vector fields in our final solution. And we write down these 5 vector fields as we did before, by writing down a basis. You choose one constant equal to 1 and the rest equal to 0, etc., etc. So then, if you choose a equal to 1, for example, and the rest equal to 0, you get the vector field equal to the following. So it turns out if a is equal to 1, xi will be equal to 1, eta will be equal to 0. So x will be equal to, very simply, d dx. Correspondingly, if you put a equal to 1 and all the constants equal to 0, the corresponding gauge term is 0. If you put b equal to 1 and the other constants equal to 0, then if you look at xi, turns out xi is cos 2x. If you look at eta, eta then is going to be minus y sine 2x. So that the vector field, let's call this one 1 and this one 2. The vector field then will be xi will be cos 2x, which is then cos 2x d dx. Eta will be minus y sine 2x, so this is minus y sine 2x d dy. And the corresponding, let's put that f1, the corresponding gauge term here, that means with a equal to 0, b equal to 1, and the other constants also equal to 0, f will be equal to minus y squared cosine 2x. So each vector field, capital X, is going to have a corresponding gauge term. So for example, if you look at this form of f here, put b equal to 1 and the rest 0, you get minus y squared cos 2x. And you do this for every one of the constants. So what I will just say here then is similarly, you get another 3 vector fields. Similarly, another 3 vector fields. So there are 5 vector fields that leave invariant the integral of L with respect to x. Now, what I'm going to discuss in the next lecture is the relationship between the vector fields we've obtained here, these 5 vector fields that leave invariant the action integral. What is the action integral? This is the action integral. So we've determined the vector fields that leave invariant this integral. In a previous chapter, we've determined the vector fields that leave invariant the differential equation y double dash plus y equal to 0. the vector field, the Lagrangian we used here was a half y dash squared minus a half y squared, and the Euler-Lagrange equation is in fact this very differential equation we discussed before. So there were vector fields that leave invariant this differential equation. We've determined the vector fields that leave invariant, these 5, this action integral. That's going to be the subject matter of the next lecture.